Hello, this is Ms. Raz, and in this video we'll discuss some of the most important takeaways from our station learning on ionic compounds. In this explain lesson, our goal is to discuss how do chemists use language to explain the formation, naming, and structure of ionic compounds. By the end of this video, you should be able to describe how the formation of an ionic compound is shown, explain how the charges predict the ratio in which elements will combine, identify the meaning of a Roman numeral and a chemical name, and you also want to be able to obtain the charge for a transition metal. In this video, you will need to use the foldable that was provided to you by your teacher. And so once you cut the foldable out, it should be double-sided. And so the first thing we're going to start with, if you turn it over, is the binary section. So you're going to open the left-hand flap, and then we're going to take some notes. So to name any ionic compound, you're going to have to place the cation first, followed by the anion. Here are some examples. If you're asked to write the chemical name from the formula, KBr would be called potassium bromide. CaI2 is known as calcium iodide. Notice that in both of these examples, the ending of the anion is changed to IDE. To write the formula for any ionic compound, you're going to identify how many of each ion is needed to have the charges add up to 0. So if you were asked to write the chemical formula from the name, like calcium sulfide, you would have Ca with a 2 plus charge and sulfide has a 2 minus charge. Those charges are obtained from the periodic table. The formula would be CaS because they combine in a 1-to-1 ratio. For aluminum oxide, again, you need to look up the charges and add just enough of each so that the charges add up to 0. The best way to think about this one is what number does both 3 and 2 go into evenly? If you said 6, you'd be right. And so that means that you need to add enough of each ion so that they add up to positive 6 and negative 6. So the formula would be Al2O3. And then finally, zinc chloride. Now you may say, how do you get the zinc charge? Well, remember, this is a transition metal. This is located right on the periodic table. And so all you'll have to do is go to that section on the periodic table and just write down the charge. And then again, just like we practiced before, the charges have to add up to 0. So you're going to have 2 chloride ions for every 1 zinc. So the formula is going to be ZnCl2. For the next part of our foldable, we're going to discuss ternary compounds. So the difference between these, just like the name implies, binary refers to 2 and ternary refers to 3 or more. To write the formula for ternary compounds, you must use parentheses when more than one polyatomic ion is needed. So for example, if you were asked to write the chemical formula from the name, calcium nitrate, the good news is this part is just like what we practiced before. We still need our charges to add up to 0. The only difference is now, because we have a polyatomic ion, we may need to add parentheses if more than one of the polyatomic ion is needed. Something like NO3- is called nitrate, and the nitrate ion has a 1- charge. So you're going to technically need 2 nitrates for every 1 calcium. So look at the way the formula is written. You'll have to put a 2 outside the parentheses. And it's kind of like the distributive property in math class. You would technically distribute the 2 to the oxygen and to the nitrogen. So it's saying that you have 2 nitrate ions for every 1 calcium. Let's take a look at ammonium phosphate. Ammonium is the only positive polyatomic ion on your periodic table. And then phosphate is PO4 3-. Not to be confused with phosphite. So be really careful. Phosphite, as you explored in the station learning, is actually PO3 3-. But it works the same exact way. Technically, you need 3 ammonium ions, but only 1 phosphate. So you wouldn't need parentheses around the phosphate, but you would need parentheses around the ammonium. So take a look at what this would look like. Let's take a look at the next one. So iron 3 hydroxide, just like we did before, we'll have to look up the charges for both. Now, you may be a little confused with what the Roman numeral means. So in the station learning, hopefully you were able to understand that the Roman numeral represents the charge on the cation. So since it's iron 3 in the name, that means that it's going to be a 3+ charge for iron. And if you look on your periodic table, you'll see that iron could be 3+ or it can be 2+. And then hydroxide is OH with a minus charge. And so for this, you'll need 3 hydroxides for every 1 iron. So the formula will be Fe parentheses OH3. Metals with more than one possible charge must include a Roman numeral in the name. That's the only way you're going to be able to differentiate what the charge on the cation is. Let's take a look at this example. So we need this cross-section of the periodic table to be able to identify what the Roman numeral is for this particular compound. So we know copper needs a Roman numeral, and the way that we know that is because we see that it has 2 possible charges. So then the second thing is we have to figure out what that Roman numeral is. So sulfate, as you know, if you turn over your periodic table, has a 2- charge. Because we know that all compounds need to be neutral, we're going to essentially have to say to ourselves, if sulfate is 2-, that means the other side has to be 2+. But here's the thing. According to the formula, there are 2 coppers. So you kind of need to say to yourself, what times 2 would give me a positive 2 charge? So if you're thinking 1, you're absolutely right. So the Roman numeral would be copper 1 sulfate. Here's another example. So if we look at nickel, we again know that it needs a Roman numeral because it has 2 possible charges, 3+ and 2+. Now something like oxalate has a 2- charge. And so if it has a 2- charge, that you again can find on your periodic table, the back of it, for the polyatomic ions, then you have to say to yourself, well, -2 times 3 will give you -6. So that means the anion side is going to have a -6 charge. That means that the cation side needs to have a +6 charge. So you need to say to yourself, what times 2, because again, there's 2 nickel in that particular formula, what times 2 would give me +6? And if you're thinking 3+, you would be right. So then that would be nickel 3 oxalate. Now we're going to open up both sections and work on some modeling. So first things first, you're asked to use electron dot structures to model the ionic compound that will form between these compounds. Now this experience is most similar to what you were doing with the chips and playing the game in the stations. So whenever we're showing modeling, we always have to start with the valence electrons. Now, you may say, what's so important about those? Well, remember, the octet rule says that atoms will tend to achieve the electron configuration of a noble gas. We said that our atoms are going to become isoelectronic with a noble gas, which just means that it has the same exact number of electrons. The octet rule helps to predict the number of electrons lost or gained in chemical reactions. So with something like magnesium and fluorine, when they combine together, we're going to start with magnesium and its electron dot structure, and then fluorine and its electron dot structure. Remember, the goal of each of these elements is to have the same configuration as a noble gas. So magnesium is going to lose 2 electrons, so it has that full valence shell and becomes isoelectronic with neon, because that's the closest noble gas. And fluorine is going to gain 1 electron, and then he also will be isoelectronic with a noble gas. The way that we show that is using arrows. So magnesium is going to give up this electron to that empty spot for fluorine, and then you can see that the fluorine has 8 electrons around it now. But then magnesium still has to lose that 1, so that's where we need to have another fluorine. And so now that electron is going to move into that spot. When this happens and these two things react, what's going to happen is you're going to form the crystal lattice. And the crystal lattice is an alternating structure of positive and negative ions. You don't want to have the ions that are both negative next to each other because that causes repulsion. So we want to show them alternating. So what we're going to have is fluorine in brackets, just like you see there, and a 1- charge outside. So the brackets indicate that the electrons belong to fluorine now. And then the 1- charge is showing that 1 electron was gained. And then after that, I'm going to put the Mg2+ next to it because magnesium lost 2 electrons. And then finally, we need our second fluorine that is converted into our fluoride ion. So again, we have our square brackets, and each of those had 8 valence electrons around it with a 1- charge. And so that's what I mean when I'm talking about alternating the ions. Let's do the next one. So this one is a little bit more of a complicated one, and you'll see why. So aluminum has 3 valence electrons and oxygen has 6. Aluminum is a metal. It's going to lose its electrons to oxygen. And think about this from an effective nuclear charge perspective. Oxygen has a greater effective nuclear charge than aluminum, so it attracts electrons more easily than aluminum does. So oxygen is going to essentially take those electrons away. So aluminum is going to be able to transfer this 1 electron to that spot and this 1 electron to that spot. So now oxygen is satisfied. It has 8 electrons around it. Aluminum, however, has 1 electron left over. So that means we have to keep going. We need to have aluminum lose all of its electrons. So in order to do that, guess what? I have to make another oxygen. So there's my other oxygen. I see now that aluminum is going to give up its electrons to the oxygen there, and then aluminum satisfied. But oh no, that next oxygen is not. So guess what? I need another aluminum. So now this electron is going to go in that open space. Now the oxygen is satisfied, but aluminum is still not quite there yet. So I need to create another oxygen, and then this electron is going to transfer into that oxygen place, and then this electron is going to transfer into that empty oxygen place. And so now, after these transfers, we are going to have to draw our alternating ions within our crystal lattice. And there's a couple of different ways to show this. So I started out with my oxide anion, where again I have the brackets around it, and again I have a 2- charge because each oxygen gained 2 electrons. I'm then going to draw my aluminum ion, and then I'm going to draw another oxide anion, and then I have another oxide anion, and then you can draw an aluminum ion. And as long as, again, these are not touching, like you don't have negative and negative together or positive and positive together, that is a completely fine alternating crystal lattice. So after all that, take a moment, reflect on these questions. Did you learn these things? I would encourage you to pause the video and read them over to make sure you're comfortable with them. Okay, chemists, that's the end of our explain video. I hope this video was helpful in understanding how to name and formulate, and also be able to draw the models for ionic compound formation. Thank you so much for watching.